So in this lecture we are going to start by a few application problems from section 1-2. So we are still in 1-2, and there we are learning about applications of trigonometry. One problem we might want to take a look at is problem 19. On this picture it says that Brian uses his vacation time to ready his lake property for summer. He wants to run a new safety line from point B on the shore to the corner of the anchor diving raft in the middle of the lake. So we have a picture like this. So here is some diving raft. Here's a current safety line. Which happens to be 40 feet long. Here's the shore. He is installing a new line. The anchor on the shore on this place is point B. The old anchor is point A, and this is set up so that this is a right angle there, and he estimates the angle from B to the corner of the raft to be 50 degrees. So we are working with the assumption that this angle is going to be about 50 degrees. The question is how much line we need, assuming that you have to add 5 extra feet on either side for tying the rope to the anchors. Okay, so what will we find for, let's consider this point, this is a diving raft, let's call it R. So we want to find the length of BR, that is the line, and then we need an additional 10 feet for tying things down. The question is, what is that going to be? Well, to simplify the problem, here we have a triangle, which is nicely enough a right triangle. This angle is 50, the opposite is 40, and what we are struggling to find is this length L. So we ask ourselves, what trig function is it? And you could have choices, but we always go with the easier ones. What trig function connects these three quantities to each other? Okay, so with respect to the angle of 50 degrees, this is going to be what? It's going to be its opposite, is that right? And this is going to be playing the role of the hypotenuse. So what function connects the opposite to hypotenuse? So we have sine of 50 degrees is equal to opposite over hypotenuse. We can multiply both sides by L, so it becomes L times sine of 50 is equal to 40 feet. So I multiply by L. Both sides are multiplied by L. This L and this L cancel each other out. So, or you simply say I cross multiply. So we need to be fast in rearranging equations which has fractions on the two sides of them. Terminology is you solving it by cross multiplication. Well, somehow you bring yourself to this stage, and then next stage we want to find L itself. I have to divide by sine of 50. So typically in high school you do like this, you actually write it out of what you are going to do. In university level courses, they kind of expect you to do that in your mind and move on to the next stage. Do whatever is comfortable for you, make sure you get the correct answer. But let me just say, as a university level expectation is that once you see this one as your starting statement, sine of 50 is 40 over L, we simply say exchange L and sine of 50. L comes here and sine of 50 goes over there. So that's the exchange of two terms in cross positions. We bypass all of this. Okay, at this stage we are just ready to use our calculator to find out what it is. So by now we know the exact answer is going to be 40 over sine of 50, and then additional 10 feet for just tying it down. So we write the exact answer, and then we go ahead use our calculator. Again, make sure you know how to use your calculator. Buy it now and keep playing with it, and make sure that you know where everything is. So this one is going to be, what do you get for this? 52.2, and then you add 10 feet to it, you make 62.2 feet. That would be our answer. Any question on that one? So, was the issue? The issue was extracting a simple triangle out of this thing. Write a trig function that connects the known quantity to the unknown quantity. Of course, we could have used cosecant, but your calculator doesn't have a cosecant. We rather go with sine, cosine, and tangent, so that we just see everything in terms of those. Another issue we raised was that from here, sine of 50 is equal to 40 over L. For a quick solution, we say exchange these two. If you wish, if you have A is equal to B over C, you can say C is equal to B over A. You can exchange these two entries. If you had more extended fraction like A over D is equal to B over C, you're allowed to exchange these two or exchange those two or bring one to the other side. A lot of things you can do with fractions. You need to be able to handle this type of equation and rearrange it quickly and confidently and solve your trig equations based on that. So this is a crucial type of expression you need to be familiar with and be able to work it out. Okay, that was problem 19. A much more extended problem that we want to talk about is problem 29, which is a quilt design problem. So we have a problem that says somebody's building a quilt, and it is looking something like this. So the quilt is divided to 12 little squares. Inside of each of these squares there is an elaborate design. What is mentioned about it is that, so we take one of these there is a circle here. Inside of that circle there are quite a few things. What we are concerned about is that there is an octagon in it. So there is shape like that, and what we are told is that each side of this octagon is 7 inches long. That's a crucial piece of information. So we are dealing with an octagon, a regular octagon, which is an 8-sided shape, and the side of octagon is 7 inches long. What we are asked for is, what are the dimensions of the quilt? Is that what we are asked for? Yes. Find the radius of this green circle, which is referred to as a circumscribed circle. And so what okay, so let's draw a bigger picture. We have a square. Inside of that square we have a circle. Well, that circle is going to have a radius r. So far, what can we tell about the size of the square? If the size of the square is s, if the side of this is s, and the radius of this thing is r, what's the connection between s and r? So the radius of the circle, let's just call it r. Side of the square is s. Why do I pay attention to the side of square? Because, well, this is going to be how many squares do we have here? So this is going to be 3s. This is going to be 4s. Dimensions of the quilt that you want to find is going to be 3 times the side of the square, and the other one is 4 times the side of square. But what do they have to do with the radius? No. What's the connection? Again, what's the connection between radius and s? Ignore everything else in this problem. Just consider square. Inside of it is a circle. Question is, yes, very good. So that's what I was searching for, is to say that, well, this is r and this is r, so 2r is same as s. Diameter of the circle is same as the length of the side of the square. So we keep that in our mind. Now, backing up now to, let me make sure this picture doesn't become too crowded. Okay, if this is an octagon, our strategy would be to do the following. Take this radius r and connect it to the length of the side of this octagon. Let's just write it here. So the side of this octagon is 7 inches. These are all the question is, if I know this side to be 7 inches, can I find a way to figure out the radius? And if I find the radius, if I double it, I'm going to find the side of the square. And once I have that, I'm going to triple it and quadruple it to find everything I want. So what is the information that we have in front of us? That this is a regular octagon. We need some information about some angle. Can anybody give a hint as to what angle are we going to find from the fact that we are dealing with a regular octagon? What does that tell us? What is it that's 45 degrees? So you say, imagine something like a pizza that is divided to 8 slices. What would be the angle at the vertex of each of these things? You say the whole circle is 360. If you divide it to 8 slices, each of them is going to be how many degrees? 45 degrees. So that is a major discovery here, that we are dealing with this 45 degrees. Now we need to work a little bit more on this thing. So let me take this picture out. So on that picture we have something looking like this. And this is the side of that octagon, which is 7. And we just discovered that this is 45 degrees. Unfortunately, this is not one of those 90-degree deals. We have to kind of extract a picture out of this that has a 90-degree angle in it. So what do we do? What's the easiest way to break this up into pieces which are right triangles as opposed to in angle like that? What do we do? You cut it in half. Very good. Cut it in half at this angle. Cutting in half by dropping the perpendicular makes these things into a right triangle. So all the machinery that we have built now is going to be useful for us. But then we have to be careful. What is this angle? 22.5 degrees. So let's redraw. So we have a right triangle where this one is 22.5. And how much is the side opposite of that? 3.5. What are we searching for? Hypotenuse. Okay, we just went through a problem exactly like this. I want to find the hypotenuse. I have this angle. What do we say? Sine of 22.5 is the opposite to hypotenuse. So hypotenuse, which is our radius, now later on in the semester we are going to find the actual exact value of this thing, but right now we just settle for approximate value. So keep that in mind, that that is how this thing came about. You might want to write on the side what the approximate number is, 3.5 over sine of 22.5 degrees. And what do you get for that? 9.15. This is inches. So what do we know now? I have the radius, therefore I have the side, which is double of this. So I'll have S is equal to 2R. Doubling this one, what do I get? 18.3 inches. So that well, that was one piece of information the text wanted. How big is the radius? Then the dimensions. On the top is 3s, which is going to be 3 times 18.3. So that is, I guess, 54.9 inches. On the other dimension is 4s. That would be 4 times 18.3. Okay. So the quilt is measuring approximately 44.9, 73.2 inches. Now you should be able to handle the problem if instead of a octagon it was some other shape. creative, make it decagon or hexagon or something. What is it that can somebody come up with a formula? The main information is this radius. So let me see if anybody wants to challenge themselves to the following. Side of a regular n-gon is D. Find the radius of its circumscribed circle. So we kind of blew everything out of the water now. It's just the most general thing you could ask. If instead of octagon, I say it's the n-gon, and instead of 7 inches, this is D. So what are we dealing with? Some sort of a shape. We don't say exactly what shape it is. We just say it has n sides. And each of these is of length d. What are we wishing? We are wishing for this radius. Let's call it r like this. So same story as before. It's a radius. We just draw some pictures so that we see what we are talking about. This is d. What is this angle? Well, what did we do for the case of an octagon? Do the same thing. 360 divided by n. So that's a vertex angle of n-gon. In this case, when you're coming out of arithmetic and going into algebra, you should get used to dealing with letters as opposed to specific numbers. You have an easy time with it. Octagon, which has 8 sides, but when we go to a general case of n-gon, we will have a little bit of a hard time with what do you mean n-gon. Your mind goes after trying to find out what n is, but that's not what we are saying. We say try to find a formula in general so that if I change the problem to a hexagon, you can answer it. If I say a decagon, you can answer it. With one single stone, you're killing all the birds that are out there. So we say n-gon, deal with all the cases all at once. So when we say 360 over n, don't get flustered as to, well, what is n? I don't know what n is. In a specific problem, you're going to find out what n is. We are just creating a general formula. Okay, this is 360 over n. What do we do next? What was our next step? We cut that in half. When we cut it in half, what becomes of this angle? How big is this one? Which is going to be 180 over n. Is it like that? Taking this thing, dividing by 2 makes 180 over n. And how about this one? This is d over 2, this is r. We still have the same thing, that sine of 180 over n is the ratio of the opposite, which is d over 2 over r. I make it nicer by writing as d over 2r. What is it that I want? I am looking for r. I bring r here and take this thing to the denominator. D over 2 sine of 180 over n. Okay, so when you want to go to engineering, you want to get used to formulas that have quite a few variables in them, not just one. So that becomes like a so-called black box formula. If you have the size of the dimension of your shape, the n-gon, and how many sides you got, this is that other information goes. You want to find the radius of the circumscribed circle. That is the formula. I don't recommend trying to memorize these things. I do recommend trying to understand where they came from, what the reasoning was. So you go through two stages. One specific problem with every number given to you. It was octagon. This was 7 inches. We worked it out. Next level up in your intellectual progress is being able to do the same thing with variables and not expecting to live with numbers all the time. So an important issue, educational issue we talked about, is moving from arithmetic to algebra. You have to convince yourself to take that step to become comfortable with variables and such, not to expect numbers. Yes? E? That's 2. Let's take a pen here. D over 2. This is D over 2. Okay. Interesting question on problem 46. Diameter of a pipe. It tells you about applications of trigonometry to designing tools for plumbing. Similar kind of thing. I encourage you to take a look at that. Okay, then try to do as many of these things as you can. You will have the payoff when you take your courses in calculus and such. You will have similar pictures, a bit more elaborate stories, and then you are expected to do a variety of things. You don't want the trigonometry to become an obstacle. That must be cleared out before you get there. Okay. Going to a much more advanced issues, which is the issue of trig functions of any angle. What do I mean, any angle? Everything we have done so far in section 1 and 2 are so-called acute angles. Acute angles are the angles that you encounter in right triangles. These are acute angles. Acute angles are the angles. Angle theta is acute if it is between 0 and 90 degrees. Or if you want to be a little bit more demanding, perhaps you might make it strict between 0 and 90, like that. Well, every now and then you have to deal with other type of angles, such as what? You know, suppose you're taking a wrench in your hand and you want to say turn it all the way here, or maybe you keep turning it. Maybe you bring the wrench down here, or maybe one of these ratchet wrenches you keep turning it. Or maybe you're talking about a steering wheel of a car, or whatever it is. The angle that you're dealing with is not necessarily always an acute angle. So how are you going to describe these type of angles? So these angles they don't fit in this type of a picture. And well, if all we were dealing with was just the angle itself, I could have found some way of handling it without getting myself into too much of a deep waters. We want to deal with the trig functions of all those angles. We have uses for trig functions of all sorts of angles that are not acute angles. What do we do then? We have to essentially redo everything from scratch. Trying to just stay in this stage of right triangles is not going to do. We have to upgrade ourselves and be ready for more abstract setting. First of all, how are we going to describe angles? An angle starts with a so-called initial side. That would be like the initial position of the wrench or whatever it is. And then you want to say turn it but also you want to say turn it in which direction. So we have the notion of a direction. So we could say turn it this way, or perhaps we want to say turn it this way. We will need to have words for what do you mean this way or that way, how to explain it. So we have a direction. Sometimes you might refer to it as orientation. Sometimes we want to refer to it as a sense. Or sometimes the word handedness comes in. If you try to buy a door, you will see immediately the guy is going to ask you, do you want a right-handed door or do you want a left-handed door? You buy the wrong door, you go home and try to put it to the frame, and then you say, well, this is opening in the wrong way. Hinges are in the wrong place, or the door is swinging the wrong way, and all of a sudden it becomes an issue. Just like trying to wear a glove for your right hand on your left hand, it's not going to feel comfortable. So, one way or another, we need to deal with that issue. How are you going to turn your wrench? Are you tightening it and breaking the pipe? Are you loosening it? You have to have your mind about it when you're dealing with that. We are going to need some sort of a convention to go by. In mathematics, we build our convention off of our coordinate system. That's what you are comfortable with from your algebra classes. So your coordinate system comes with an x and y direction. As you turn from x toward y, from horizontal to vertical, that is the angle that we are going to refer to as a positive direction or counterclockwise direction. If you turn your wrench in this direction, I'm going to count the angle as a positive quantity. If you decide to turn it this way, I'm going to consider it as a negative angle. Okay, so this is positive, this is negative. This one, we are going to refer to it as a counterclockwise, and this is going to be, of course, clockwise. Okay, next issue is that, well, you are going to stop. So first we put our initial angle on the x-axis, and then we have a so-called terminal side. Terminal side, and between them we have an opening angle. It could be like this, it could be like that, it could be, perhaps we turn like this, or it could be that I started from here, went all the way around, came back, and then made the full rotation and went a little bit extra. In high school, you learn that there is a name for this one. What do you call this type of angles? These are obtuse angles. But since we are dealing with so many type of angles, they don't really give it a name. Sometimes they might have a name for this thing, like reflex angles or something. We don't really emphasize we don't emphasize the names as much as we are going to emphasize the following. We go back to our coordinate system. In algebra, we learn to refer to this section by a particular name. What do we call it? Yeah, this is a quadrant. Quadrant 1, that is where your acute angles are going to happen. And this is quadrant 2, and then you have a quadrant 3, and then you have quadrant 4. And by the time you come back, you say you have made one full rotation, and then your terminal side is in quadrant 1. Somehow you have to give information about how many times you have turned. Picture by itself doesn't tell you, because you could have thought about it as if you have gone through this blue angle. You could have thought about it as if you have gone through this black angle. It could be this green angle. All of them are possibilities, and all of them end up with the same terminal side. We are going to call these things coterminal. So angles that start from the same place and at the same spot are called coterminal angles, and they are obviously not necessarily identical. They could be quite different. Okay, let's go ahead and practice a little bit about this idea we had. Specify the location of terminal side of each angle. Choose from quadrant 1, 2, 3, 4. So let's start. 30 degrees. Remember, we are starting from standard position. Standard position meaning you start from the x-axis, and then you go and then you stop. 30 degrees, of course, we are still in acute region, acute angle region. That is the quadrant 1. Is that right? How about 120 degrees? So let's practice this thing. 120. Obviously, we have passed 90. What's the next milestone? What would be this one? If I make it all the way, is 180. So if I'm between 90 and 180, I'm in such a region. Such a region means I am in quadrant 2. How about 210? So if this is 180, what's the angle down here? If I come here, I've gone through 3 right angles. That makes this 270. So if my angle is between 180 and 270, I'm stuck in quadrant 3. So this is in quadrant 3. What if I am at 330? So this is 270. If I keep going, I make a full circle. By the time I come back, I have made it to how many? So this was 0, 360. So if you are between 270 and 360, you have an angle that is in quadrant 4. Okay, let's go through some negative angles. What about minus 30? So if I go the other way, let's see, different picture. If you want to go the other way, this is 0, this is minus 90, minus 180, minus 270. By the time you have made it back here is minus 360. So if you have an angle of minus 30, you are in quadrant 4. If you are angle of minus 120, you have made it here. So you are in quadrant 3. If you are at minus 210, you have made it here. So it's quadrant 2. Minus 330, you are here. That is, you started, turned around, you came to quadrant 1. It becomes a little bit tricky if you are given some arbitrary angle, and there are plenty of exercises you are going to have that are going to ask you questions like that. Suppose an angle is like 10,000 degrees. What do you do there? It's a little bit harder than this. What would you suggest we do?
Divide by 360.
Okay, so it could be some screw or something that has been turning and turning and turning. You have to figure out how many times you turned, and then separate the full rotation from whatever is left, and whatever is left you treat it this way. So there was a good answer, which is figure out how many full rotations you have made. There are other possibilities, but here to get it started, 10,000 divided by 360. So you say 10,000 divided by 360. Your calculator helps you say, okay, 27. That's 27 full rounds. So Take 10,000 divided by 360, you get 27.7, etc. So this is 27. You take 27 multiplied by 360, of course, and you get 9,720. You see what is left? Well, what is left? I guess 280. So we say 10,000 degrees is made out of 27 rotations, full rotations of each of them 360, and then you're left with 280 degrees. Well, where is 280? Quadrant 4. So that tells you where the wrench is going to stop. This is quadrant 4. So this is full rotations. This is number of full rotations. If the angle was negative, you have to be a little bit more careful as to what you're doing, but the idea is the same. Okay, we didn't get to really cover everything here, but you're looking at something. Yes. The question is, how do you define sine, cosine, and tangent if you don't have a triangle, if you cannot talk about the ratio of opposite to hypotenuse or this or that? You don't have those things in front of you. What do? Let's just mention a couple of these things, and the rest of it we are going to leave for next time. Again, we are going to make use of our skill in algebra. Say, let's go back to that familiar surrounding that we were in the first quadrant. This was some angle theta. This was some radius r, or the hypotenuse is r. In the Cartesian, you call this one x coordinate from here to here, and this one is called, what coordinate is that? That's the y. So that point comes with a label which is x, y coordinates of this point. Now, if I were to ask you what is sine of theta, what would you say it is? Y over r. Now, y over r for us meant, this meant opposite, this meant hypotenuse. But when you are in a coordinate system, you don't need to call them opposite or hypotenuse. You can just call them y coordinate and the radius. So that's the main clue. That's what holds section 1.3 together. You give up the ideas, simple ideas from geometry. You say, let's go with coordinates. I have x, y coordinates and the distance from the origin. I can always talk about what's the y coordinate of some point, what's the distance from the origin. So I can always make sense of what's the sine of an angle. So how about cosine of theta? X over r. What about tangent of theta? Y over x. What about cosecant of theta? What about secant of theta? R over x. What about cotangent of theta? Adjacent to hypotenuse. Now, we are not using these terminology anymore. We are just using the coordinates. And for any point we have coordinates, we can always find out these ratios, and we can find out what their sine and cosines are. So that is what we are going to start with on Wednesday. Take it from there. So you want to read section 1.3, start the problems. Perhaps by Friday we are going to be done with that.